Okay, moving on to the second application of using the first law of thermodynamics in case of ideal gases is a reversible isothermal expansion or compression. Now, we have learned about the nature of reversible process in an earlier video. What are the different assumptions that are there in a reversible process, and how like a reversible process takes place in infinite steps, and how it can be reversed back at every step, and all those things. Okay. Now, an isothermal process is a process in which the temperature is constant. So the dT is equal to 0. Now, an expansion or compression, we know how the volumes change. Now, for this process, the first law remains the same, right? So let's write down the first law. So dE is equal to del Q minus del W. Now, we know that the del T is 0. So there is no change in temperature. So when there is no change in temperature, the internal energy also remains constant, because we know what is the meaning of temperature. Temperature is the average kinetic energy, right? So the internal energy, if the dT is 0, dE automatically becomes 0. So if there is no change in temperature, there is no change in the internal energy. Okay. Now, if this becomes 0, this whole thing simplifies to del Q becomes equal to del W. Now let's see what happens in compression and expansion. So if we take the case of expansion, we know that del V is a positive number, right? And work done is positive in expansion, because the force and the displacement are in the same direction. So the del W becomes greater than 0. So when del W becomes greater than 0, what will happen to del Q? Now, del Q will automatically become greater than 0. And so this is expansion, and this greater than 0 means that this is an endothermic process, right? So this is absorbing heat. Absorbs heat. Let's look into the opposite, which is very easy. So if you have compression, you have del W as negative. When del W is negative, del Q becomes negative. This is an exothermic process. And heat is released, right? So there's a relationship between expansion. So whenever you expand, it absorbs heat, and whenever you compress, you have heat released and you have an exothermic process. Okay? Now, based on this, let's find out, with the help of a PV diagram, what happens. Now, you know that this is an isothermal process. So we have seen these kind of like isothermal relationship once before in Boyle's law, right? So in an isothermal process, it is something like this, right? So let's assume this is 1, this is a 2, the temperature is constant, and let's assume this is V1 and this is V2. Now, we know that dE is 0, but we know that there is some amount of work that is being done when a gas moves from state 1 to state 2 with its temperature constant. We would like to find out what that amount of work is. Okay. Now, so to find out the amount of work, we will integrate dW from state 1 to state 2, right? Now, this becomes P dV from V1 to V2. Now, the problem with this is P is changing in here. So we want to substitute P in this equation with something which is a function of V so that we can integrate that function. Now, we know for an ideal gas, PV is equal to nRT. Therefore, P is nRT by V. So we'll be substituting this in here. Okay? So we'll be substituting the value of P here. This becomes nRT being constant. So temperature was constant. Number of gases remains constant. Number of moles of gas remains constant. R is the universal gas constant. So nRT can come out of the integral sign, and you get 1 by V dV integrated from V1 to V2. Now we know that what is the integration of 1 by V times dV? So dV by V is natural log of V. So this becomes nRT ln V, and this the lower limit is 1, the higher limit is 2. So it goes from V1 to V2. So this becomes a definite integral, right? So what will be the value of this? nRT ln natural log of V2 by V1. Okay, now this is the value of W, and let's call this equation 20. Now we know how that whenever you have an isothermal expansion, you know that the dE is 0, but how will you calculate the amount of heat or the amount of work done? Using this equation. So if you find W, that will be the same amount of Q in the, it will be equal to the value of the heat. So heat and work, if you calculate one, you can calculate the other using this equation. Okay. Now, for this, we knew that dE was equal to 0, right? Now, we can understand it in a similar fashion by using CV. Now we know what CV was. This was del E by del T at constant volume, right? Now you can find out dE by getting this dt to the other side. So CV dt. Now since this dt becomes 0, dE becomes 0. Okay. Similarly, for Cp, this will have a similar fate in which delta H becomes 0, because this dt goes to this side. There's a similar fate in here, so dH becomes 0, right? In here, both CV, Cp gave the values for, like, we tried to come up with the value of dE and dH independently from this using the values of CV and Cp, and we got dE and dH both equal to 0, right? So this was the case for the isothermal expansion and compression.